Space is full of mysteries, but none of them bend the rules of reality quite like black holes. They warp space, slow time, erase information, and challenge everything we think we know about physics. And the strangest part is this: black holes aren't science fiction. They're real objects shaping our universe right now, holding galaxies together and bending light like it's nothing. Today, we're going to peel back the layers of one of the most misunderstood phenomena in the cosmos, and take a beginner-friendly dive into what black holes actually are, how they form, and what really happens at the edge of no return. So sit back, relax, and let's unravel one of the universe's wildest secrets. Black holes are some of the strangest and most misunderstood objects in the universe. They sound like something out of science fiction, invisible cosmic monsters that swallow everything around them. But the truth is far more fascinating than the myths. Because black holes aren't really holes, they don't suck things in like vacuum cleaners, and they're not gateways to other dimensions. At least, not in any way we currently understand. And the way they affect time-space and even information itself is so strange that the moment you get close to one, the rules of the universe begin to behave differently. So today, we're going to unpack all the weirdness. We'll look at what a black hole actually is, why it forms. What happens if you fall into one? What strange behavior unfolds around its boundaries? And how something that doesn't let light escape can still be one of the brightest objects in the cosmos. And by the end, you might realize that black holes aren't the villains of the universe. They're more like cosmic engines, shaping galaxies, bending time, and pushing physics to its absolute limit. Let's start with the beginning. What exactly is a black hole? A black hole begins as a star. But not just any star. It has to be a very massive star, something at least 20 times more massive than our sun. Massive stars live fast and die young. They spend millions of years burning through their nuclear fuel, fusing hydrogen into helium, then helium into heavier elements. But one day, they run out of fuel. And when they do, gravity wins. The star collapses. Not gently, but violently. The core implodes, the outer layers detonate in a supernova, and what's left behind is an object so dense, so compact, that the atoms inside it are crushed beyond recognition. If the remnant is massive enough, even the forces that normally resist collapse. Things like electron pressure and neutron pressure can't stop gravity anymore. The collapse continues until the entire core becomes smaller than a city, then smaller than a mountain, then smaller than a grain of sand. And eventually, it becomes a single point. Or at least that's what our math tells us. A point with zero size and infinite density. A place where the laws of physics break. We call this point the singularity. But the singularity isn't the part we actually interact with. The important part is the invisible boundary surrounding it. This boundary is called the event horizon, and it's one of the most misunderstood concepts in all of physics. The event horizon isn't a physical surface. If you flew toward it, you wouldn't crash into anything. It's simply the place where escape becomes impossible. Cross that boundary, and even traveling at the speed of light won't get you back out. That's why black holes are black, not because they eat light, but because light can't escape once it crosses the horizon. But here's the twist outside the event horizon. Black holes don't behave in any spooky or magical way. From a distance, a black hole's gravity works just like the gravity of any other object of the same mass. If our sun were suddenly replaced by a black hole with the exact same mass, Earth wouldn't get sucked in. It would keep orbiting in the same path completely unaffected, aside from the small issue of losing all sunlight and freezing. But gravitationally, we'd be fine. So where do all the dramatic effects you've heard about actually come from? The extreme behavior of black holes happens near the event horizon, where gravity is so strong that space and time become distorted. And I mean literally distorted. According to Einstein's theory of general relativity mass curve spacetime, the more mass, the deeper the curve. And black holes create the deepest wells of spacetime that can exist in the universe. If you imagine space as a stretched rubber sheet, a star is like a bowling ball that sinks into the sheet. A black hole, though, is like replacing that bowling ball with a dense sphere of lead, then shrinking it smaller and smaller and smaller without removing any of the mass. The rubber sheet doesn't just sag, it plunges into what looks like a bottomless pit. At the bottom is the singularity, and the event horizon is the rim of that pit. Let's explore some of the strange things that happen near that rim. The first effect is time dilation. Near a black hole, time slows down compared to places farther away. The closer you get to the event horizon, the slower your clock runs. This isn't science fiction. This is experimentally confirmed physics. If you were drifting toward a black hole, time for you would feel normal. But from the perspective of a distant observer, you would appear to slow down. At the event horizon, your movement would seem to freeze entirely. You would fade dim and eventually vanish, never quite crossing the horizon in their view. But that's not what you would experience. From your perspective, you would fall right in. And depending on the size of the black hole, you might not even feel anything unusual at the moment you cross the horizon. If the black hole is huge, millions or billions of times the mass of the sun, the tidal forces at the event horizon are surprisingly gentle. But as you get deeper, the difference in gravitational pull between your head and your feet becomes enormous. Your body stretches. The process is nicknamed spaghettification, and unfortunately, it's exactly what it sounds like. Eventually, the gravitational gradient becomes so extreme that your atoms are torn apart. It's not a pleasant way to go. But this image of black holes as destructive monsters overshadows a more interesting truth. Black holes can actually be brilliant. And I mean brilliant in the literal sense. Some of the brightest objects in the universe quasars are powered by black holes. How is that possible if nothing can escape? Because the brightness doesn't come from the black hole itself. It comes from the material around it. When gas dust and stars fall toward a black hole, they swirl into a disk called an accretion disk. Friction heats this disk to millions of degrees. The swirling material glows in X-rays and even gamma rays. This glow can outshine entire galaxies. Then magnetic fields twist the inflowing material, launching massive jets of energy that blast thousands of light years into space. These jets are so powerful that they can shape entire galaxies. We've even photographed a black hole. In 2019, the Event Horizon Telescope produced the first real image of the shadow of a black hole in the galaxy M87. It looks like a glowing donut with a dark center. That dark region isn't the black hole itself. It's the shadow of the region where light bends so much that it misses our telescopes. Seeing that image was like humanity touching the unknown with its bare hands. It proved that black holes aren't just theoretical. They're real, and they're stranger than we expected. Now let's go deeper into the weirdness. For decades, we assumed black holes were perfect cosmic prisons, swallowing everything in their path and keeping it forever. But in 1974, Stephen Hawking discovered something shocking. Black holes can evaporate. They can shrink. And eventually they can disappear. This happens through something called Hawking radiation. The explanation is rooted in quantum mechanics. The vacuum of space isn't really empty. Pairs of particles and antiparticles constantly appear and annihilate each other. But near the event horizon, one of these particles can fall into the black hole while the other escapes. From the outside, it looks like the black hole is emitting particles. Over incredibly long timescales, this causes the black hole to lose mass. A giant black hole takes longer than the lifetime of the universe to evaporate. But a small black hole could disappear faster in a final burst of energy. This discovery created one of the biggest puzzles in physics, the black hole information paradox. If a black hole evaporates, what happens to the information about what fell in? In quantum physics, information can't be destroyed. But black holes seem to erase it. Does it escape in the Hawking radiation? Is it stored on the surface of the event horizon? Does the interior somehow preserve it? Or does our understanding of physics itself need to change? This paradox is still unsolved. It's one of the greatest mysteries in science today. But while we debate the fate of information, black holes continue shaping the universe in ways we can see. At the center of nearly every large galaxy, there's a supermassive black hole. The Milky Way has 1,2 Sagittarius A star, about 4 million times the mass of the Sun. These black holes anchor galaxies, influencing the motion of stars and the structure of spiral arms. Without them, galaxies might look nothing like they do today. Black holes also help form stars. Their jets and radiation can compress nearby gas clouds, triggering star formation. In a strange way, black holes both destroy and create. They tear stars apart, but they also help new stars ignite. They bend space-twist time and radiate energy. They shape galaxies, spark the birth of stars, and challenge our understanding of physics. They're not villains, they're fundamental. So let's step back and summarize this cosmic paradox. A black hole begins as a dying star collapses into a point of infinite density and becomes wrapped in an invisible boundary called the event horizon. It warps space and time to such extremes that time slows near it, and nothing, not even light, can escape once it crosses the boundary. But from outside, black holes can be brilliant, powering the brightest objects in the universe. They can evaporate through Hawking radiation. They may hold the key to quantum gravity. And they sit at the centers of galaxies, shaping the evolution of the cosmos itself. We went from thinking black holes were monsters to understanding they're engines of creation and laboratories of fundamental physics. And the closer we study them, the more they reveal how little we know. Because black holes aren't just objects. They're boundaries between what we understand and what we don't. Between classical physics and quantum physics. Between the visible universe and the invisible rules underneath it. Every time we learn something new about black holes, we learn something new about the universe. And every time they surprise us, they push us a little closer to understanding the deepest questions in science. So the next time you picture a black hole, don't imagine a cosmic vacuum cleaner. Imagine a place where space collapses, time slows, matter stretches, light curves, energy explodes, and the laws of physics stand on the edge of breaking. Imagine the strangest object the universe has ever made. And remember that somewhere out there, millions of light years away, a black hole is silently shaping stars, galaxies, and maybe even the future of our understanding. And that is how black holes really work. Black holes are more than cosmic curiosities. They're natural experiments running in the depths of space, pushing physics to extremes we can't create on Earth. They shape galaxies, ignite stars, bend time, and challenge the limits of human knowledge. And even with everything we've learned, black holes still hold onto their deepest secrets. Every answer leads to a new question, and every discovery pushes us closer to understanding the universe we live in. If you enjoyed this breakdown and want to explore more strange and fascinating corners of science, feel free to subscribe and join us for the next exploration. Until then, keep wondering, keep questioning, and remember, the universe is far stranger and far more beautiful than it first appears.